Hello everybody, thanks for joining me again. This is going to be video number 2 in this series I'm putting together. The first video, if you haven't seen it, I'll link it right here, okay, so you can go watch that if you think it would help you catch up to what we're doing here. The first video is on average modeling of a boost converter. You've seen it before, tons of people have done it, but it was the setup for some of the more advanced techniques we're going to start today. And the technique we're focusing on today in video 2 is state space. I'm going to show you how to set up state space, what it means, what each of the variables is for, the state space matrices, etc. And then we'll discuss a little bit like how could this be used. But again, what we're doing even with this video, honestly, is setting up for more advanced techniques to come. How do we solve state space in a more elegant and useful way, which we'll discuss in the future. But anyways, also if you wanna download again this PDF that I'm showing right here, said this in the last video, but this is a summary of kind of all the techniques I'm going to be going over in this little mini course or this video series to walk you through it. So feel free to do that. The link's in the description. And without delaying anymore, I'll jump into the derivation. So here at the beginning of this video, I've included some of the same graphics as last time. I have the boost converter, I have the D interval, interval 1, and the D prime interval, interval 2. And we need to derive the equations for each interval. So for D, interval 1, we'll write the KVL and KCL equations. That's going to be VL equals VN minus IL RL. And we'll simplify that till we have DIL over DT isolated. And then we'll do the same thing for the KCL equation till we have DVC over DT isolated. And then we'll look at interval 2. We'll do the same thing and we'll isolate DIL over DT and DVC over DT. So we want the derivatives isolated. And then what's notable here is in the average model, once we had these equations underlined here in yellow, what we did was we said, okay, well, because it's in steady state, I'm going to assume that the voltage on the inductor averages and the current in the capacitor averages to 0. And we said, okay, so I'll say D times this and D prime times this, add them together, etc., etc. So we're not doing that here. We're going to take a different approach, but it's important to say that up until this point, the equations are the exact same, but how we handle them from here on is going to be different with the state space approach. So let me just explain the basic form of state space. You have dx over dt, the derivative of x equals ax plus bu. And then you have y equals cx plus du. This top one here is the main equation, and we're probably going to spend most of our time in the video with this equation. The bottom one I would consider a helper equation. Effectively, you can use the bottom equation to pull any signals from your system that aren't in the state vector. We'll worry about that later, but you may be asking now, what is the state vector? And basically, the state vector, denoted x, is going to be your capacitor voltages and inductor currents, or you could just say any element in the system that's dependent on its history. So the voltage in a capacitor, you can only know that if you know all the current that's ever gone through the capacitor. Similarly, the current in an inductor, only if you know the voltage the inductor's been exposed to. U is the input vector. So this is sources. In the example we're showing here, that's going to be Vn. Basically, these are things that don't change with time. This thing right here, U of t, is approximately U, capital U. What I'm saying is these are technically time dependent on a mathematical level, but we approximate them as constant, okay? And in the circuit, Vn is already approximated as constant, so this is a really good approximation for the way we handle circuits to begin with. Y is the output vector. Basically, this is non-state vector signals that the user wants to extract. I'm probably not going over that much in this video, but it is in that PDF I said you could download. And then matrices A, B, C, and D basically say how thing 1 affects thing 2. So A is multiplied by X. So what A is saying is I'm describing how X affects dx dt, how the state vector affects the derivative of the state vector. B is going to say how U, the input vector, affects the derivative of the state vector, affects dx dt. C, similarly, will say, hey, I'm describing how X affects Y, and D, how U affects Y. Okay, so that's the basic form of state space in a nutshell. And you'll notice that I'm kind of lazy with these parentheses T, close parentheses terms. Basically, the state vector, the output vector, even the stuff over here on the left, the equations we derived, a lot of them are time dependent, but I'm too lazy to write it. So sorry about that, but just be aware of it moving forward. Okay, so now look back at the original circuit and realize that we have two switches, Q1 and Q2, okay? But then in the subintervals, there's no switches. That's because in either subinterval, we assume that the switch is either completely on or completely off, and is ideal in those intervals. Basically, that approximation means that either interval is made of nothing but linear components, which is exactly why at the beginning of the video we were able to describe either subinterval with these differential equations. That's the reason we can build state space equations, is because every interval in the circuit is made up of linear components that we can describe in these differential equations. So now if I want to define the A matrix for interval 1, then the first thing I have to do is define the state vector. Here I'm going to define it as VC and then IL. You'll notice that this is different than the PDF I gave you guys. I put IL on top in the PDF, so now you have two different derivations of the same thing. Either form is valid. The state vector, you can choose the order arbitrarily at your own will. So I've chosen it this way. That means that in order to find what matrix A1 is, I have to put VC and IL up top in this order, and then I have to put the derivative of VC and the derivative of IL down the side in the same order, okay? And then to decide what goes in any of these indices, I'm going to look back over the differential equations we created, and I'm going to say, oh, look right here. dVC dt is dependent on VC by this term minus 1 over C R out, and it has no dependence on IL. Similarly, I'm going to look at the other differential equation and say dIL dt is dependent on VC, 0, has no dependence, and it's dependent on IL by this term minus RL over L. Now if I want to define B1, so that's the B matrix for interval 1, I have to make sure I've first defined the input vector. Here, as we already talked about, the input vector is going to be Vn, and that means similar to A1, I'm going to write Vn at the top, and then I've got dVC over dt and dIL over dt on the sides, and I'm going to say Vn. I'm going to look back at my differential equations again for interval 1 and see dVC over dt is not dependent on Vn, so that's going to be 0, and then dIL over dt is dependent on Vn by this term 1 over L. I now have my state vector, my input vector, that's x and u, and then I've got A1 and B1. So the A and B matrices that describe interval 1. Now basically all I'm going to do is move down to the other pair of differential equations I have for interval 2, and I'm going to repeat the process, and I'm going to create A sub 2 and B sub 2, and that's the A and B matrices for interval 2. Now basically I've got A1 B1 and A2 B2, and then I've defined x and u over here. Right, so now I have the state space model for this main equation that I told you about earlier, and that's a big deal. Congratulations, you just derived your first state space model. So now that we have the state space model for interval 1 and interval 2, I'm just going to take all this stuff and I'm going to consolidate it, right? So let me move this stuff up to the top and reintroduce some waveforms here. And the question now is going to be, okay, that's great, we derived it, but what can I do with it? Okay, so just follow me for a second with a thought experiment. Assume in these waveforms, I know one point in time. So I know the value of VC and the value of IL. That means I can take the interval 1 equations, because these values are in interval 1, and I can say A sub 1 times the VC and IL values that I have, multiply them times B1 times Vn. What it will return is dVC over dt. So effectively, if I have values of the states in the circuit, I can predict the state derivatives at that point. Now that's a big deal. For this circuit, it may not seem immediately apparent why it's a big deal, because the slopes for a boost converter with all the approximations that we're applying, the slopes are effectively constant. The derivative, you know, it's just straight lines. So it doesn't seem like that big of a deal. But follow me for a second on a thought experiment. Assume that one of your states, okay, is not constant. Assume it looks more sinusoidal or has a bunch of dynamics. Now, if I know the value at one point, right, and I can determine the slope, let's say I just guess and follow that slope and assume the next point is on that slope. And then I do the same thing. I find the slope at that point, then guess the next one, so on and so forth. You can see how this begins to look like the waveform itself, okay? Now, let's assume that I actually decrease the step size. It's basically the sample time, okay? You start at the exact same point with the exact same slope, but the next guess is closer to the previous point. Now you see how much closer the guessed line or the calculated line is to the actual value. This is how simulators work. Basically what you're doing is linearizing around an operating point, moving forward some small time step, and then linearizing around that one and moving forward again. Okay, so it's powerful because it's how simulators work. So I'm going to jump into MATLAB and I'm going to show you guys a little bit of how this works. Basically how we can take state space, which is just a beautiful way of organizing the differential equations for every linear interval in a power electronic circuit, and how we can basically create a simulator out of this. And then again, moving forward in the next videos, we're gonna do something more complicated. I'll show you a more elegant solution, but for now we'll jump over to MATLAB. I'll show you a quick example. This is the same program that I showed you guys on the last video. I've got some circuit parameters. And I've added this tick parameter, which just basically allows me to look at the execution times. And here, I'm actually not going to skip the state space description. Now we're going to look at this, right? So this is how we defined everything. We've got the input vector, Vn. We've implicitly defined the state vector as ILVC. And then in the PDF, I defined the output vector as the voltage across the parasitic resistance. A1, B1, A2, B2, and then in the again in the PDF I used that second state space equation. So when I run all this, it's going to just give me these state space matrices. Steady state stuff we went over, the averaging stuff we went over in the last video, and then down here what I'm showing is how I can iteratively locate steady state using the simulation kind of approach. So what I'm saying is I've got 1,000 samples per period. Remember, we want a high resolution sampling time or a small time step. I'm initializing my state vector with some values. Here I'm using the average values, and then a couple more initialization steps. And I'm just going to let this loop run until the state vector meets some error criteria, meaning it's in steady state. It starts and ends at the same point in the period. So the beginning of the period and the end of the period are roughly the same value. That means it's in steady state. And then I'm looking at the time, deciding which interval I'm in, and then evaluating the slope, and then using that projection, that linear projection, to find the next point, etc. So this is not the best way to find steady state, but I'll run it and show you guys the result. So after letting this run for a second, you can see I killed the operation here because it was taking too long, and printed the execution time, and it was over 4 minutes to find steady state. Now, I told you this wasn't the best method, so let's just look at the waveform of the current here. Let's plot that, see what it looked like. Oh, need a new figure. Okay, so you can see that the current was oscillating and approaching some steady state, right? But it never got within the tolerance I specified here. So the system never basically flagged that it was in steady state. Similarly, we can look at the voltage. It was doing the same thing. It was oscillating and it was approaching some steady state value, but it never got within this tolerance. So it took 4 minutes. We were approaching some steady state value, but we never got there because we had to hit some tolerance. And again, this took so long because we have 1,000 samples per period, and it takes multiple periods to get within some acceptable tolerance and consider ourselves in steady state. So overall, simulating like this to find steady state just costs a lot of time, right? So the last thing I'll show you guys is under this iterative steady state code that took forever to run, I've got one more thing. I've got how we would use state space to build the waveforms. This is effectively the same thing as iteratively finding the steady state, except I'm starting with what I assume the steady state is and defining how many waveforms, like how many periods I want the code to build. I'm still using 1,000 samples, so I have a high resolution sampling rate, and I'm still referencing the fundamental state space equation to build the waveforms, and then I'm just printing it out. So let me run this, and what you'll see over here is we have inductor current with the ripple like we'd expect, same for output voltage. So it looks good, except you'll notice the output voltage doesn't look like it's in steady state. It looks like it's slowly rising. And actually, if you were to zoom in on the inductor current, you'd see something similar. It's not quite in steady state either. That's because when I initialize here, I initialize the waveform with these values, which I derived using the averaging equation. So actually for this type of simulation, these are not the correct initializations. So I'm actually not initializing with the steady state values. To have the correct steady state values, I would have to let the previous code run for a long time until it converged. And then I would put those values here, and then the graphs, the plots would look like they were in steady state. So anyways, you can tell all this stuff works. It's getting at the correct ideas. It shows the ripple, but it's a little bit clunky. It takes time. You have to do a lot of calculations. So we'll look in upcoming videos at more elegant ways to approach this. Closed form solution for the state space models, and things like that. So tune in to the next videos, and we'll see you there. Thanks for watching.